Okay, so now we're going to talk about the squeeze theorem finally. Sorry I was not able to get this out earlier, but anyway, so we've got a member. I'm going to talk about the squeeze theorem, so feel free if you're out there to go ahead and ask questions, chime in. Hopefully you can hear me, but there's a chat function as well, but you could just talk to me too. So, but it is going to be recorded, so that's my full disclosure there. But anyway, we're going to talk about the squeeze theorem, which just says let f, g, and h be defined on some open interval I except possibly at A itself. So anyway, we're back into the limits where we don't need to be defined at that point. But we're also going to let F be less than or equal to G, which is less than or equal to H on that same interval. So of course, I haven't said it, but F, G, and H are all functions, which by using those letters is obvious in what I write. But anyway, if we have that, then what we're going to have is that the limit as x approaches a of f of x is going to be less than or equal to the limit as x approaches a of g of x, which is going to be less than or equal to the limit as x approaches a of h of x. So none of this is real hard. Seems to make sense that that would be the case. But the reality is, if I can show that this is some specific limit L1, and this also equals some specific limit L1, then by default, I'm going to be able to guarantee that this is the one in the middle for g of x is going to be some specific limit L1. So if I have two on the outside that I can handle, basically, or that I know what those limits are, then maybe one that I'm not really sure, if I can guarantee that it lies strictly on or in between these functions on that interval except for at A, then I'm going to be able to find that limit by utilizing the squeeze theorem. So let's just draw a picture or a visual of what this looks like. I'm going to try and use different colors here. So let me go to that. So I'll use black for kind of my base XY axis here. Here's my point x equals a. So remember, when I'm going to take the limit, I approach from both sides, from the left and from the right. But then I'll use f. We'll use red, which is, I don't know, fuchsia is kind of pink, so I don't know if I have that color. But anyway, there's F. Well, that has a limit as x approaches a of where this open dot is. So I'm going to assume that I'm not defined at a, but this is the limit for my function f by my graph here. So there's my function. Remember, the function's got to pass the vertical line test. And then for g, I'll use green. I'll just say, hey, here's g of x. So that's my function g of x. Here's going to be my limit for g, that function g as x approaches a from both sides. And then for h, I'm going to use the hue of blue. And so maybe look something like this. But notice that on some open interval, by the way, let me get, this is the limit for function h there as well. But anyway, what we notice is there is some open interval where f of x is less than or equal to g of x, which is less than or equal to h of x, which for some reason I got to draw that on there. But also, that's going to imply that the limit as x approaches a of f of x, which is actually L sub f, so is going to be less than or equal to the limit for g, the limit as x approaches a of g of x, which is going to be less than or equal to the limit as x approaches a of h of x. So all of these, this inequality will hold here. Okay, so it's pretty obvious based on this picture. So what we really want to do then is we want to look at, this doesn't do us a lot of good. This is kind of a duh thing. But at the same point in time, we can kind of leverage this. And I drew this up the other day in class. But if I have, as I approach A, if they all approach the same limit, I call it L sum 1. I'm just going to call it L for the limit. But if I still have my function f and I'm not going to be defined there, but if this is my function f of x, and that's less than or equal to my function g of x on that on some open interval, which is less than or equal to my function h of x. Okay, so there's h of x. I forgot to put in g of x, but green is g of x. But anyway, so here I have that f of x is less than or equal to g of x is less than or equal to h of x. But all of those have, I didn't draw my red function very well, so kind of make that a little bolder here. But they're both going into that limit there, L. So all of my functions have the limit as x approaches a from both sides equaling a. So if I know what the limit as x approaches f, let's see, I get my screen's changing on me. I know you can't see my screen getting bigger or smaller, but hopefully I'm going to be able to draw here. So if I know what the limit as x approaches a of f of x is, and I know what the limit as x approaches a of g of x of h of x is, and they're both the same thing, but I know g is in the middle, then, you know, so if this is, we called it L, and this one's L, but they're both L, then I'm going to be able to be guaranteed that because one is less than the other is less than the other, that the limit as x approaches a of g of x is going to be in between there. And then also, because this is less than or equal than that, which is less than or equal to that, this is also going to exist and equal that same limit L. So the question is, how do we do this for a specific problem? So let me show you one, so that hopefully that will help you with that number 30 on your homework. Okay, so in this case, so here's an example. I want to show that the limit as x approaches 0 of the absolute value of x times sine 1 over x exists and equals 0. Okay, so the reality is that graph might be hard to come up with, but you know, if we have a graphing calculator, we may be able to do this. But I want to show this by the squeeze theorem. So I'm going to use the squeeze theorem on this. So the question is, all right, what I'm trying to find here is the limit as x approaches 0 of this thing. So the reality is I want to put that in the middle, right? And then I want something on the right of this and on the left of this. And so let's find out what we could do. So we want to squeeze the function x sine 1 over absolute value of x sine 1 over x between two functions that we know the limit. Okay, which would be f and h. But anyway, so between two functions where we know the limit to be the same thing. So how are we going to do that? So first of all, what do you know about sine of anything? We know, whoops, got to get back where I can write. We know that sine of anything is, I'll call it sine of t. We know that sine of t is between -1 and 1, right? Because here's what the sine graph looks like. It goes like this, and it would keep going, right? And it would never get above 1 on top and never get below -1 on the bottom. So what do I know about the absolute value? So the absolute value of sine of anything, I'll just call it sine of t, is going to be less than or equal to 1 for the top side, but if I'm taking absolute value, it can't be negative. So I do know that the absolute value of the sine of anything is between 0, on or in between 0 and 1, right? So basically, I would just flip the negative part, become positive if I'm taking the absolute value of it. So what can I say then? For this particular problem that I have, I can say that we know that the absolute value of the sine of 1 over x Well, first of all, I know that that's going to be less than or equal to 1, but I also know that that's going to be greater than or equal to 0, right? So then what can I do? Now that's not quite the one that I have. The one that I have is x times sine 1 over x. So really what I could do to each part here is I could multiply, and since I was using specific colors for the functions, but I'm going to multiply this times the absolute value of x. Well, if I do that in the middle, I've got to do it to all parts. So this is going to be the absolute value of x times 0, and this is going to be the absolute value of x times 1. So if I multiply all of those by the absolute value of x, by the way, what happens to my inequalities here? For my inequalities, those are actually going to stay the same since absolute value of x is greater than or equal to 0 by definition, right? So I'm not multiplying by a negative number. I'm actually multiplying by a positive number, or 0, if x happens to be 0. But can x equal 0? No, because then I wouldn't be able to take the sign. So let me just erase this. I have to erase that. By the way, we're taking the limit as x approaches 0 anyway, but does not, so it won't touch 0. So anyway, since absolute value of x is greater than 0, the inequality is going to hold. So what does this imply? And I'll just keep it here. What's the absolute value of x times 0? Well, that's 0, right? And it's going to be less than or equal because that would carry down. Now the absolute value of a times the absolute value of b is the absolute value of a times b. So this is the absolute value of x sine 1 over x, which is what I am trying to evaluate the limit of, which is less than, and then the absolute value of x times 1 is the absolute value of x, right? So I do have a chain link inequality here where really if we were looking at f, g, and h, I was using f of x would be equal to 0, h of x would be equal to the absolute value of x, and then of course g of x is the one I want, is in between. But I have that f of x is less than or equal to g of x is less than or equal to h of x. And then, so what do I know? And I'm defined on some open interval, right, around 0 for this function. So the domain of this function, the domain of g, is all reals excluding 0, right? So the domain of g, if I'm looking at g is this middle one, is all reals excluding 0. Well, negative infinity to not including 0, union not including 0 to infinity is some open interval containing a except possibly a itself. A is 0 because that's the limit that we're approaching as x approaches 0. Anyway, so we have this. So what do we know? By the squeeze theorem, so we have that. Let's just, I should be able to remember that, hopefully. But, so let me clear this. It hasn't kept me from drawing yet. So this implies that the limit as x approaches 0 of all three of those is going to hold the same inequality then by the squeeze theorem, right? So by the squeeze theorem, well, I don't need that yet. We just know that this is less than or equal to the limit as x approaches 0 of the absolute value of x sine 1 over x, which is less than or equal to the limit as x approaches 0 of the absolute value of x, which on my screen it looks like I'm running out of room. Sorry if it doesn't look like that to you. So anyway, but once again, I used red for fuchsia or whatever. But anyway, what is the limit as x approaches 0 of 0? Well, the limit of a constant is constant, that's 0, right? And what it, whoops, on this I was using blue for my h of x, right? But what's this one? The limit as x approaches 0 of the absolute value of x. Well, we know what that graph looks like, right? That was a base graph shift. So as I approach 0 from the right, I approach a height of 0. As I approach, my x's approach 0 from the left, I approach a height of 0. So this is also equal to 0. So 0 is less than or equal to this limit, which is less than or equal to 0. So what can I say? Therefore, this middle one, the limit as x approaches 0 of the absolute value of x sine 1 over x, whoops, absolute value of that, equals 0 by the squeeze theorem. So I squeezed it in between two functions that I knew, okay, on the outer edges, but I know that that had to be on or in between those. And in this case, it had to be on the limit of 0 for both of those. So that's how we utilize the squeeze theorem on that, is to find two functions that we can handle, where one is less than or equal to it, the other one is, and then the other one's bigger than or equal to it, so this one's in between. And if those end up being the same value on the outside, and this has to be on or in between, then we know that that has the same value as well. Okay, so hopefully that's a clear example of how we do that. And then if I were to, just so you know, I think if we were to graph that function, if I had, I was calling it g of x is the absolute value of x sine 1 over x. You all have a graphing calculator or graphing tool, but I think if we have, if this is the absolute value y equals x and y equals minus x lines, I think what happens instead of you know, sine getting smaller like this, and then as you get right getting bigger, it makes them all positive. So I think what happens is it's this getting smaller inside of there. But anyway, coming up and touching that. But as I approach from the right and from the left, I'm approaching a height of 0 because it starts bouncing in a smaller window there that has a height that approaches 0. So I believe that's what it looks like, but you can verify that on your graphing calculator. So hopefully that's enough on that one, but I am going to do another example here. So if you want to drop off, you can. If you would rather stick around and see one more example that's a little more involved, then we can do that too. So now I'm going to say where we don't have the absolute value, and then what could happen is the inequality could flip. And so we could have something like that too. So let's look at an example. If I want to find the limit as x approaches 0 of just x sine 1 over x. Okay, so here we got to be a little bit careful because we do not have the absolute value signs. Okay, so this is the function in between, not really sure how it works, you know, stuff like that. So let's look at two different cases. So let's look at case 1. Case 1 would be the easier case. That's when x is greater than 0. So when x is greater than 0, how is this going to work? We're going to do it similar to what we just did. So I'm going to say, hey, I know that sine of one, this is what we know that sine of anything is less than or equal to 1 and greater than or equal to minus 1, right? Because sine of anything, you know, goes like this in both directions, but the max height is 1, the min height is -1, so we know that this is bounded, right? So we know that that's bounded, and then what can I do? I can multiply everything by x. So if I multiply by x times x times x, I got to do it to each part. But since x is greater than 0, what happens to the inequality? The inequality is going to hold and be the same. So this will imply that minus x is less than or equal to x sine x is less than or equal to x. And then I can take the limit just like I did before. And of course, for some reason, it is not letting me write. So I'm going to try it again. Nope. So I was doing so good. So now I'm going to try and get off of there, go back into it, see. When it does this to me, it actually lets you write. So I don't know how to, let's see. All right, let me see. It's not letting me do it. So anyway, to finish that out, basically it would be just like what we did before, where the limit as x approaches 0. Now I would have minus x. Actually, I'm going to go to the camera because I'm in my room. So I can do this. I can get the camera on, share my camera, and show you the board and me. And I'm still dressed up. I think I showered this week. So let me, where'd I go? How come it, all right. Can you see me? How's it going? So can't wait to see everyone in the morning. How is my board crooked? My table must be crooked. But anyway, so obviously this is a distorted view of a camera, probably because it's turned. I don't know. How's that? So I got to the edge. I can start about here, and let's make a little note of how far over I can go. So anyway, what I had there is I had that -1 was less than or equal to sine 1 over x, which was less than or equal to 1, because sine of anything is bounded by -1 and 1. And then I just multiplied everything through by x with case 1, x is greater than 0. Okay, so I multiply everything times x there, and I get minus x is less than or equal to x sine 1 over x, which is less than or equal to x. And then now, so that implies that, but now I can say that the limit as x approaches 0 of each one, the inequality is going to hold true. So x sine 1 over x, which is what I'm looking for, is the one in the middle, and that's less than or equal to the limit as x approaches 0 of x on the right. Well, so here's what I know. I know that the one on the left, this is a polynomial or a line, so I can just plug it in, right? So this equals 0, and this one equals 0. So what do I know about the one in the middle, which is the one I was looking for? So this equals 0 by the squeeze theorem. Okay, so that's 1/2 of the argument, and that's when x is greater than 0. So hopefully you can see that. I don't know if I can scoot that a little closer. Maybe see that a little bit better. Anyway, going there. So now let's try it again and do case 2. So let me go to case 2, and I'm just going to erase this now. Case 2 is when x is less than 0. And if x is less than 0, and I multiply, first of all, I still have that -1 is less than or equal to sine 1 over x, which is less than or equal to 1, because sine of anything is bounded by plus and minus 1. But now if I multiply through by x, what type of number am I multiplying by? X is negative, so I'm multiplying by a negative number for all three of these. So the inequality is now going to flip and become greater than and greater than there. So minus x is greater than or equal to x sine x is greater than or equal to x. So then what changes here? I'm going to rewrite this backwards. So I'm going to rewrite the chain link inequality. Instead of being greater than and greater than, I'm going to flip it around. So this says that, reading it right to left, x is less than or equal to x sine 1 over x is less than or equal to minus x now, in this case. So that implies that the limit as x approaches 0 of each one of x is less than or equal to the limit as x approaches 0 of the middle one, which is what I want, which is less than or equal to the limit as x approaches 0 of minus x. And then, of course, I know that as x approaches 0, what's x approach? 0, that's the identity, or you can say it's a polynomial, plug it in. And that one's 0. Therefore, for case 2, this one also equals 0 by the squeeze theorem. So the only difference here is we had to pay attention to the inequality flips because of multiplying by a negative number everywhere there. So it's going to flip or reverse the inequality. So that's really the moral of the story with the squeeze theorem. So there's a couple examples that helps you with that. Any questions? If you do, I could answer them now. Okay, you all have my contact information, so go ahead and reach out. So I'm gonna stop this so that it'll go into the recordings. You can watch it again as many times as you want, which hopefully that's not more than once or so. But anyway, good luck and reach out with questions.